Okay, let's get started. This shouldn't take more than 30 minutes or so. So this new lab involves going over the binary search tree and Avl tree code in closer detail. In the previous lab, we used binary search tree and Avl tree, but we had to change minimally the code. We didn't require a detailed understanding of exactly all the details involved in insertion and deletion. In fact, there is no deletion involved. Only in insertion we needed to add an additional field that maintains line numbers in which the key occurs. This time we have to understand the code in a little more detail. Even here, you don't need to rework the entire code, but just need to add a few additional features to the code. So basically, what is the problem? The problem we are trying to solve is the following. We know that a binary search tree can efficiently support the dictionary operations, namely search, insert, and delete. Right? These are the most important operations. In fact, with these operations, we can, for example, efficiently sort. Right? How do you sort n numbers given dictionary operations? Well, with only search, insert, and delete may not be easy, but if you need one additional functionality, namely delete min, okay, then it should be very easy to sort n number. How do you do that? So in other words, you are given n numbers in a file. Right? They are completely arbitrary. Our goal is to get all those numbers written back into a new file, but this time all the keys have to be in ascending order. Okay? But you cannot write any code other than just calling these functions. I mean, when I say you cannot write any code, obviously, you cannot solve any problem without writing code. But what I mean is, essentially, you are restricted to calling the supporting function, namely search, insert, delete, and delete min. How do you put these things together to efficiently sort the numbers? Yes?
Does delete min return the key that was deleted?
Yeah, delete min return the key deleted.
You can repetitively delete the minimum of the tree after you've inserted it to it?
Right, so initially you insert all the n keys into an initially empty tree, right? And then perform a series of delete mins. So n insertion followed by n delete mins will get the entire array sorted, right? And using an Avl tree, what is the complexity of this? Well, each operation we know can be done in log n time. Well, we didn't quite complete that discussion yesterday, on Wednesday, right? We finished looking at the code for insertion. In fact, we haven't even finished the discussion of deletion, which is what we are going to do today. But let's actually go back to the insertion, right? How do we know that it can be done in log n time? Well, first of all, we know that an Avl tree with n nodes is guaranteed to have height log n, right? Because we proved that. Okay, so, but when you do an insertion, if you follow the code, you'll see that basically the code involves examining at each node. Well, you start at the root node, you're looking for the key x, right? Depending on whether the key is less or greater than, you're going to recursively make a call to perform an insertion on the left subtree or right subtree, right? So that means you're just walking down the tree until you come to a node where you found that node is a pivot node, right? Because at every point, after you do this insertion, you're going to check if the height of the left and right subtrees differ by more than 2. Well, this may not be completely obvious, so let's actually open the code and so this is the code for insert, right? So you want to insert a key X into a tree rooted at node T, right? It's an Avl Tree node, and the key X is being inserted. If X is a null, then you simply call a constructor to create a node with the key X, right? Else, if X is less than the root node, then you recursively insert on the left subtree, or you insert on the right subtree, okay? And then you call the function to the balance, okay? So what is the total complexity of this? Well, you can count this by simply looking at the cost involved in executing this code plus the cost involved in executing the balance function, right? The cost of this itself is order h. Why? Because you're just walking down the tree, right? From the root to a leaf, right? So it's order h. And then you have the call to the balance function. And now we can look at what happens with the balance. I think that's in the previous slide. Okay. That is the balance function, right? So if the tree is null, you don't need to do anything because empty tree is balanced, right? Otherwise you check. If the height of the left subtree minus height of the right subtree is greater than the allowed imbalance, then you decide whether you should do a double rotation or a single rotation, and then you perform that. Else you do exactly the same thing on the other side. So this is the LL and LR rotation. This is RR and RL rotation. And then finally you adjust the height, okay? So what is the cost involved in this? There's no loop here, right? There's no recursion either, right? All you're doing here is you're calling one of these four possible functions followed by this. The cost of implementing this is a constant, right? Because note that even though you're making a function call, this function call works in constant time. In fact, what is the code for computing the height? It's a one-line code, right? It just checks if the tree is null. If the tree is null, then it returns -1. Otherwise, it just goes and grabs that height field from that node. Okay, so it's constant. Okay, and then the rotate with the left child. This is a single rotation case, and we saw that the total number of instructions there is something like 5 or 6. If you're not sure about that, let's actually go and inspect the code. So there it is, right? So this is the code for single left rotation, and this involves 1, 2, 3, 4, 5, and 6 instructions. So it's a constant, okay? And what about double rotation? Well, double rotation involves 2 calls to single rotation that you can again see in the next slide. So you see, in order to do a double rotation with the left child, you just make 2 single rotations. So the complexity of this is a constant. This is the same constant. So the total number of instructions is twice that number, 12 or whatever, depending on how you count it. So the whole idea, therefore, is that the total complexity of executing the balance itself is a constant. It's not even O of H, it's a constant, right? Because every one of these instructions can be executed in a constant number of instructions independent of the height of the tree. Now, this is not an important fact in the case of insertion. Because in the case of insertion, we could afford to spend even order H time, till the total cost of insertion will be only order H. Why? It's because while you execute the code for insertion, how many times would we encounter this balancing? In other words, note that the code physically has only one copy of balance, right? But potentially this balance could appear multiple times. Why? Because this insert makes a recursive call to this insert, which in turn comes and hits this statement, right? Therefore, potentially how many times could you be doing the balancing? Height times, right? Because each time it could potentially cause this. But in the case of insertion, that will never happen. Why? It will only happen once. We argued this in great detail in the lecture, right? Remember, what we saw was that once we identify the pivot node and then perform a rotation, not only it balances that node, but it restores the height back to what it was before the insertion. And therefore, you never have to do this more than once, okay? And therefore, the overall complexity of insertion is order H. And furthermore, the number of times you have to call the balance function is only a constant. But this is not going to be the case of deletion. In case of deletion, what's going to happen is that this balance at one node will trigger a balance at other nodes repetitively, and therefore potentially you will end up making H calls to balance. But you're still fine. Why? Because the complexity of balance itself is a constant. And therefore, even though you are invoking this balance function H times, it's H times a constant, which is order H. This is why deletion, we haven't looked at the code of deletion in detail, but we'll still do that in a moment. But the net result is that the overall complexity of both insertion and deletion is order log n, and therefore we can sort n keys in n log n time. Okay? So this is a second n log n algorithm for sorting. The first one is merge sort, which we looked at, right? It has complexity order n log n, even though I didn't prove it. Okay, so this is our second n log n algorithm. We're going to see 2 more n log n algorithms for sorting in future. One is the heap sort, and then finally we are going to see quick sort, which again, it's not in the worst case, it's not n log n. In the worst case, it's n squared, but most of the time it's going to be n log n. Okay, so before we look at the code for deletion, let's talk about the project itself. So we began by saying that dictionary operations are quite powerful, can do things like sorting, can allow us to do things like sorting. But still, dictionary operations themselves are not powerful enough to collect statistics from a large data set. So for example, if I have a large number of keys that I've built into a binary search tree, and if I want to know what is the median key, right? What is the definition of median?
That's the middle value.
Right, middle value. That is, if you have a million keys, the key whose rank is, say, 500,000. The key which has the property that there are as many keys smaller than it as there are larger. That's called the median key. It's, in fact, one of the most important numbers that represents a collection, right? more important than mean. Just adding them and dividing by the population gives what is called average, right? Which is an important statistic, but even more important than mean is the median, okay? So how would you find the median of n keys built into a binary search tree or an AVL tree for that matter? Can you do that very fast? Well, of course, once you've built it into an AVL tree, you can perform a series of delete mins n over 2 times. And then the last time, n over 2 times do a delete min, that is going to be the median, right? Is that a good algorithm for finding the median? It's really a terrible algorithm. In fact, what will be the complexity of finding the median using repeated delete mins n over 2 times? Then log n, right? Why? Because each delete min costs log n time, and you have to do it n over 2 times. So it's n over 2 times log n, which is order n log n, right? So investing n log n time for finding the median is extremely high. What I'm looking for, what can we aim for? Log n, right? We cannot do better than log n. I don't think so, because you want to find the minimum key takes log n time. Just walking via a series of left links, right? It'll take log n time. But log n seems to be a very ambitious goal, right? But it turns out that that can be done very easily by augmenting the data structure. So there's a whole concept called augmenting a data structure. So what is an augmentation of a data structure? Well, you increase the functionality of a data structure by adding extra fields, which is exactly what we did with the indexing lab, right? We added an extra field, which is a pointer to a vector that kept track of all the various line numbers where the document appeared. Another way to extend a binary search tree is what? Suppose I want to store duplicate keys. In other words, suppose my data is not a set, but it's a multi-set, which means same key can appear many, many times. Okay. What kind of an adaptation should I do to a binary search tree that will allow us to do this?
Okay, what was the question? I'm sorry.
Question is, with a binary search tree, I want to be able to maintain a multi-set. So the same key might appear, say, 10 times. Another key might appear 3 times. Another key might appear once. And normally a binary search tree will not.
I mean, similar to how we implemented the line numbers in the index, could you just
So what do? You could
add another variable to your struct or class.
Right. What will that variable hold?
The number of occurrences.
Number of occurrences. Simply, instead of a vector, you just have a single int called count, which will be incremented every time the same key is inserted. A second time it will become 2, and you insert a third time it will become 3, and so on. Is that clear? So now we can. This is called an augmentation of a data structure, right? So this time, what we are going to do is augment the binary search tree by adding a field called size, which is the number of nodes in the subtree rooted at that node. So let's look at an AVL tree. Is this an AVL tree? Okay, I'm going to place some keys here: 14, 21, 30, 36, 41, 45. Okay. So if you want to augment this, we need to have an extra field which will hold the size information. To avoid cluttering the node itself, I'm going to write the size field with red marker on the outside. So what will be the number associated with this node? No, size.
Oh, size.
6. What will be the number of this node? 3. Right. So that's the kind of information that's going to be attached to each node. Now, why is this helpful? assume that we have implemented our binary search tree or Avl tree with this augmented structure in each node. How will that help us to determine, for example, the median? In fact, let's say more generally, I want to know what is the fourth largest key.
Fourth largest size. Would it be the fourth largest size or no?
Yeah, fourth largest. So for example, in this case, what is the fourth largest key? Let's talk in terms of the fourth smallest. That may be easier to think about. So what is the fourth smallest key? 36, right? What is the smallest key? 14. Second smallest? 21. Third smallest? 30. Fourth smallest? 36. Okay? So what we want is, we want to create a new function called key of rank. So if I now call key of rank t comma 4, what I'm asking is, give me the fourth smallest key in the tree rooted at node t. Is that clear? So this second parameter is the rank. And what we are trying to return is the key of that particular rank. So in particular, if you want median, what should be the parameter we should set here? Right, look at the root node and divide it by 2. That parameter will then give us the median. Is that clear? Okay. Now the question is this: how do you determine the key of a given rank using this additional information? I mean, more generally, it could be any number k, okay? Doesn't have to be n over 2. Say, I want to know what is the, let's look at this particular key. What will allow me to determine what is the fourth smallest key? Well, look at the size of the left subtree. Size of the left subtree is 3, yes.
Yeah, so if n over 2 is your median, then...
No, don't think in terms of median. I talked about median only because it's the most important thing. Let's talk in more general terms. We are not looking for the median. We are looking for the kth smallest, where k is an arbitrary number.
Well, then you can look at the size of the its left subtree from the root, and if that's less than the number that you're looking for, then it must...
So in this case, for example, it's 4, right?
Right, and there's...
Look at the left subtree, its size is
3. Instead
3,
of
and therefore in this case we immediately can conclude that the fourth smallest one is what? The root node, right? So what if I'm looking for the fifth smallest? Again, you look at the size of the left subtree, that is 3, and then you add a 1 for 4, the root, that's 4. This number is still bigger than that sum. Therefore, we know that the fifth smallest key has to be where? On the right subtree. Therefore, I continue recursively. And then when you make the call, what parameter should I pass? So more generally, if I'm looking at k here, and let's say that the size of the left subtree is, let's say, I, then what should be the recursive call? 2. It should make a call to the right subtree. Then what should be the number I should pass here? This is the key. K minus I.
And then minus 1.
Minus 1. Is that clear? In other words, the kth smallest in the entire tree is going to be the k minus 1 minus I, k minus I minus 1th smallest tree on the right subtree. Is everyone clear about this? This is not a hard concept. All we are saying is, from the fact that, well, when is this a valid call? We know that k is bigger than I. Okay? Right? In fact, we know, is it bigger than I or is it bigger than I plus 1? In fact, it's bigger than I plus 1. Right? So we are looking at three different cases, right? What is I? I is the size of the left subtree. Suppose k is equal to I plus 1. Then what can you say?
No, if it's equal, it'd be the root.
It is the root. If k is equal to I plus 1, then the kth smallest key in the entire tree is the root key. Is this clear? Because there are exactly I trees on the I keys on the left subtree. Therefore, the I plus 1, the smallest key, is the root key, which is exactly equal to k, right? It's clear. So in this case, we can simply report the root key. Yeah. So what is the second case? The second case is where k is greater than I plus 1. In this case, you simply make this recursive call. Right? What is the third case? K is less than I plus 1. Okay, in this case, what do you do? Recursively simply call the function with the k pointer left, and how should the second parameter be adjusted? What should be passed as the second argument? Okay, this is not clear. Let's actually take a concrete example. So let's take k equal to 2 in this tree, in this example. Okay. So I'm looking for the second smallest key in the entire tree. And to do this, I'm going to make a recursive call. Now I want to find the some key in this left subtree. What should be how should the rank be changed? Well, when I use the word changed, I'm not necessarily suggesting that it has to be actually changed. Yes?
T minus 1, minus the root node.
I mean, T is a pointer.
Oh, right.
T is a pointer to a node.
Oh,
Cannot be
left.
T minus 1. T is not a number.
Or it'd be T left.
That's already, I told you, it's I. So my question is, I'm sorry, so key of rank, T of left. Please tell me what should be in the blank.
K minus 1.
You are saying k minus 1. Any other? Yes. Okay, so some. Okay, any other candidate? Any other choice? Okay, there are at least two competing claims here. Which is the correct one? It is k. It's not k minus 1, because look at this example, right? What is the second smallest key in this entire tree? 21. What is the second smallest key in the subtree? Second smallest key in the subtree is rooted at this node. Therefore, what should be the call here? Just k. I don't know, this is not a hard thing, okay? In other words, if the left subtree has more than k keys, then the kth smallest key in the entire tree is the same as the kth smallest key in the left subtree, right? Because all other keys are bigger. See, they don't matter. The kth smallest key still remains the kth smallest key in that subtree. Is this clear? This is not a hard concept. Maybe you're just not following what is going on. So I'm a little bit concerned. So I hope you can understand this. So I'm going to now show you the actual pseudocode. So I have to switch back to the this. Okay, so this is what you're talking about. We're talking about key of rank function, which you're going to implement. And the pseudocode is here. Okay. It's clear. So, right? So key of rank k comma t. Sorry for the mix-up. I wrote there t comma k, but here it's k comma t. But I hope it's not it's clear. So if tree is null or k is out of range, then return null. Okay. Note also that this function is not assuming that k is a valid number. K is an integer, but it could be out of range. What does that mean? So for example, if the tree had 100 keys, and if I'm asking you for a key of rank 101 or 200, that doesn't exist, right? Because there are only 100 keys. Therefore, only meaningful rank values are 1 through 100. So anything that's out of range has to be dealt by returning a null pointer. Okay. Okay. So the first thing you're going to do is, if the size of the left subtree is exactly equal to k minus 1, then you return a pointer to the root node, which is exactly what we discussed there, right? So that's the case where k is equal to the size of the left subtree plus 1. Okay? So in this case, simply return a pointer to the root node. Else, if the size of the left subtree is greater than or equal to k, which means it's actually greater than k minus 1, right? Then you recursively compute the key of the rank k in the left subtree. Else, you return the key of rank k minus the left subtree size minus 1, which is exactly what we said here, k minus I minus 1, comma. Right. So exactly what we discussed here is just presented in the form of the pseudocode. Any questions about this? In other words, my point is, even if you didn't understand everything here, you can mechanically turn this into pseudocode. But what I'm asking you to do is understand it before you do that, right? Okay. This is a very powerful idea, right? By simply adding an extra field called size, now we can determine the key of any given rank in what complexity? What is the complexity of this? It's order h, right? Because at every node, we do a constant amount of work and then transferring the job recursively to the next level, and the next level, and so on. Therefore, in the worst case, you will be walking down the tree at most by performing order h operations, right? So its complexity is order h, right? Okay, now let's look at the inverse problem. The inverse problem, what we want is, we are given a key now, and we want to know what is the rank of that key. So it's like this. Suppose I've entered the score of all the students into a binary search tree, right? I can ask, what is the median score? That is key of rank question. But I can also type in the name of one specific person, George, and ask, what was the rank of George's score in that test, right? That's the key of rank. So I give you a number. Like, for example, I can ask, who got the highest score? I can pass one, I'm sorry, no. If you want to find who got the highest score, you have to use this function. If you want to know what is the score, what is the rank of a particular individual, then I can use this, right? Okay, so how do we do this now? So I'm given a key x. I want to know what is the rank of this key. Well, first of all, if the tree is empty, then you're going to return a 0. So any key that's not in the tree should result in the number 0 being returned, right? Because 0 is not a valid choice, and so I'll know that by returning 0, that key is not there. Okay. If the key x is less than the root key, Then what do? So for example, let's take this tree, right? Okay, say I give you a key like 30 and I ask, what is the rank of 30? How do I determine that? By just looking at the root node. So I started the root, I'm looking for the key, the rank of the key 30, right? But 36 is at the root node, 36 is larger than 30. Therefore, what do you know about the rank of the key 30? Well, first of all, because the root node has 36, 30 has to appear where? In the left subtree, right? Okay. So I make a recursive call, but then how does the rank change as a result of moving to the left subtree? Okay, what is the rank of 30 in the whole tree? 3. What is the rank of 30 in the left subtree? 3. Rank of 30 remains unchanged. 30 is still the largest key in the left subtree, its rank remains unchanged, right? In other words, when you move to the left subtree, you're throwing out all the keys that are bigger than or equal to the root key, 36 and above. None of them are going to have an impact on the rank of 30, right? Because they're all bigger, they appear after 30. Therefore, the rank of 30 is not going to change. Therefore, you simply recursively compute the rank of X in the left subtree. Okay, what about a key like 41? Okay. How do you determine the key of rank of 41? Let's again go back. Start from the root. Okay, I want to determine the rank of 41. Since 41 is bigger than 36, we know that 41 is going to appear on the right subtree, right? Okay. Now, what is the overall rank of 41 in the whole tree?
Dude, come away from the door before the laser blinds you.
Oh,
It's reflecting off the board and hitting right
oh
where
really?
you
Okay,
are.
that's fine. Okay. What is the rank of 41 in the whole tree? Rank of 41. 5. Okay. So rank of 41 is 5. What is the rank of 41 in the right subtree? 1. What is the relationship? I want to... How did you get to... What is the connection between the rank of 41 in the right subtree and the rank of 41 in the whole tree?
1 plus.
Just 1 plus? No, it was 6 in the whole tree. I'm sorry, it was 5 in the whole tree. It is 1 on the right subtree. It dropped by how much? Dropped from 5 to 1.
So it's the size of the entire tree minus
Size of the left subtree plus 1. Those are all the keys that got dropped. Okay, I mean, these are all not very difficult concepts. So let's try to understand what is going on here. So this is the entire sorted array, right? So this is the root key, okay? This is the key X, okay? So the question is this. Suppose I index the whole array from 1 here, and let's say the index of this is K, right? Is clear? Instead, suppose I start indexing from this point. In other words, I drop all these things, just drop off this whole thing, and then if I start indexing from this point, and let's say now I get the index K prime. What is the connection between K and K prime? So I'm indexing the same array in 2 ways. One, by starting at the leftmost position, numbering 1, 2 like this. The second case, I drop a whole segment, I start my indexing from here. And let's say the number here, first of all, what is this number here? This is the root key, right? This is R at the root. Therefore, what is this number here? This is the size of? How many keys are here? If I take all the keys in the tree and put it in the sorted order, and if this is the root key, what are all these keys?
Size of root maps.
These are all the keys in the left subtree. Therefore, the number of keys here is the size of the left subtree. Okay? Therefore, how many elements am I dropping in my new indexing? What is the relationship between the two indexing? How much shift have I done? Size of left subtree plus 1. Therefore, what is K prime? K prime is K minus size of left subtree minus 1. Right? That's exactly what we saw here, right? Look at, for example, 41. What is the rank of 41 in the entire tree? One more time, let's do this. What is the rank of 41 in the whole tree? 5. What is the rank of 41 on the right subtree? 1. What is the difference? 5 minus 1 is what? 4. And that 4 came from where? Size of the left subtree, 3 plus 1. That's exactly what this formula is saying. Okay. Okay. So this means that all you have to do is, in this case, okay. So in this case, else, you're going to return 1 plus the size of the left subtree plus the rank of x in the right subtree. This is clear. In other words, recursive call will return what value? It will return k prime, right? But we need to return k. Therefore, k is k prime plus the size of the left subtree plus 1. That's exactly what this is saying. Return 1 plus size of the left subtree plus the rank of the key k x in the right subtree. That's it. Okay. Again, it's very easy to see that the total complexity of this is order h. Therefore, if I built an Avl tree with million keys, and if I now want to know what is the rank of a specific key, I can just call this function and it can do this in order h times, okay? Which is order log n times, which is extremely good. So in other words, if you are, for example, trying to track some important statistical parameters, like for example, how the median of NASDAQ index or H&P or some other data, temperature taken over multiple cities as it changes from day to day, right? If you want to create new data that shows how this temperature, what are the median temperature across various cities over a long period of time, you can do all these things and collect data very rapidly and do plotting and so on, right? These things are extremely important now because this is what is the basis for the big data science that people are now talking about, right? So, collecting large, manipulating large data sets is giving some unprecedented insight into physical processes, economic processes, political processes, and so on, right? So these kinds of functions are going to play a very important role in very rapidly collecting these kinds of data. But this is only showing how to do this under what assumption. In other words, in all of these, we have made one crucial assumption, namely that we already have this field called size that I can make use of. So in order to make these functions work efficiently, now what do you need to do? You have to go back to the binary search tree and Avl tree code and update it accordingly. We need to now add the size field. That's the easy part, right? All you have to do is what? In the constructor, have an extra field called size, right? And then set it to 1 initially because a single node tree has 1 key. Okay, that's the easy part. But then when a deletion or insertion happens, you need to adjust the size, right? So that's the second part of this exercise. So you need to go back to the function for inserting or deleting and update the size field as required. So now let's look at insertion, right? So in the case of binary search tree, if you want to insert a key, now what do we need to do? Well, if the tree is null, then you have to call a constructor, and now all you have to do is augment this constructor to have the size field set to 1. Okay? Now, there's one important issue here. Now, what we are going to do is we are going to assume that the insert is going to return a Boolean that says whether the insertion was successful or not. Right? Remember, somebody could call an insert function to insert a key that already exists in the tree. Right? In which case, what should be our action? Not do anything, because by definition, a binary search tree cannot have more than one occurrence of the same key. Right? But but now what we have to make sure is, in case where an attempt to insert the same key was made, we have to return a Boolean variable that says false, because our attempt to insert did not succeed. Why is this important? Normally when you do insert, this is not critical. Right? In other words, the caller of the function getting notified whether the attempt to insert was successful or not is a good thing, but not a critical thing. But here it is critical. Why is this critical? Yes?
If it returns false, you have to update the frequency of the key.
Remember, it's not frequency we are talking about, it is the size we are talking about. Okay? So let's say, for example, attempt to insert at the root node triggered a call to insert on the left subtree. Okay. So in other words, let's say the root contained 25 and you are trying to insert the key 20. So what would you do? You would now make a recursive call to insert 20 on the left subtree. Okay. And that call is now going to tell me back whether the insertion was successful or not. If the insertion was not successful, what does that mean? That means 20 was already in the tree. Therefore, should I now change the size at this root node? No, because 20 was already there. I didn't add anything. But if the recursive call returned true, then what should I do to that node, to the root node? I should add 1 to the size. Why? Because the subtree rooted in that node has gone up by 1. Because 20 was now inserted in the left subtree. Right? Okay. Now we might ask, how about adding 1 to every node on that path from the root to the leaf? Well, you don't need to do that because recursion will do that. Okay, this is the nice thing about recursion, right? So you only have to deal with the root node. Okay, is that clear? So that's all this code is doing. So if x is less than t pointer key, then recursively call to insert x on the left subtree. If the call succeeded, then you have to increment the size at the root node. And you have to return true, right? Because you have to report to the next level, saying that the insertion was successful. Else, if x is equal to the root key, then what do you have to do? Return false. Because in this case, you know that x is already there, therefore you are notifying that the insertion failed. Else, handle insertion on the right subtree in a way similar to the left subtree. So that's all there is to insertion. Deletion is done in a similar fashion. So I'm not going to walk through this pseudocode systematically because it's again very straightforward. All I've done here is I've just adapted the deletion that we talked about with the binary search tree to handle the size information. Okay, now how about Avl tree? Okay, so Avl tree we have to do a similar thing, right? Insertion and deletion. Okay. Let's first look at the code for deletion without worrying about the size information. Okay? How is the deletion done in an Avl tree? So here is the function for remove, okay, delete. Turns out quite remarkably that this code, without this last line here, right, balance, this code is identical to deleting in a binary search tree. It's exactly the same thing. Okay? Remember various things? The tree is now don't return, just return, don't do anything because the key you're trying to remove doesn't exist. Else, if x is less than the root node, then recursively delete on the left subtree. Else, if it is greater, remove it from the right subtree. else, this else here corresponds to the case where the key you're trying to delete is at this node, T, and therefore now you consider further cases. The first case is where both of this node has both left and right subtrees, and therefore in this case what you do is you do a find min on the right subtree and then delete that. I'm sorry, not delete it, get that key and then replace the key at this node by that key, and then you call the function remove to remove that key from the right subtree. Otherwise, this is what we call the shortcutting step, right? You simply make the parent of this node to point to the only child that this exists. Okay, so that's exactly the same as the code that we saw for the binary search tree, except that we've added one extra line here that says, after doing all these things, you have to do a balance at this node, because potentially what you might have done is you're at the node T, right? It has both non-empty subtrees, and you have deleted the X from one of the subtrees, and by doing so, you might have reduced the size difference between the left subtree, right and left subtrees by 2, right? In other words, the difference is already 1, and if you deleted one of the keys here, now the difference might have become 2, and just calling balance will take care of it. Okay. So this is a very nice way to organize this code, because just by adding that one single statement, which we already know how to do, because this balance function is exactly the same for both insertion and deletion. Okay. Yes.
How does that shortcut function in your else statement work with the question mark and the colon?
Yeah, we went through this many times.
Oh, sorry, I was
Okay. Does anyone want to explain how this works?
Now, okay, so within the parentheses, you have a condition. If it's true or false, it'll, if true, return false with a colon. If the first part of the colon is true, and the second is false.
Okay.
If condition
So T is assigned to this variable if this condition is true, otherwise T is assigned to this.
Okay, it makes sense.
Okay, so now we have to see what additional thing that we need to do to the size field in this balance function, okay? So as a general rule, I mean, this project is intended for you to think a little bit about this code, so I don't want to give you every detail. In fact, the handout already tells a lot of things, right? This is the general rule that you have to remember, right? In other words, whenever the size, the height field is adjusted, right? You know that immediately that node could also potentially undergo some change in the size field. So you have to go and adjust that. So let's very quickly go back to the code that implements balance. Okay. In this entire code, there are calls to these 4 functions here, right? Rotate with left child, double with left child, rotate with right child, double with right child. There are 4 of these function calls, right? Each one of them, in turn, is going to involve some height adjustments, okay? We'll go back to that later on, okay, and see how, in those cases, the size adjustment have to be done. But for now, let's not worry about that, because they will take care of themselves. What is the other place where a height adjustment is actually done? Is there a height adjustment done in this statement? Is there a height adjustment that's being done in this statement? These are all just reading the height information and doing some action based on it. They are not updating the height. Is that clear? There's a difference between reading some data and updating the data. Here we are just reading the height information. Is that clear? So in all of these places, height is not being adjusted, being accessed, not being updated. Therefore, we don't need to worry about anything. The only place where the height is adjusted is here, right? Okay. So as a rule of thumb, we know that whenever the height is adjusted, we need to also adjust the size. So can you tell me one additional line of code here after this t pointer height equals ... I want to write one more statement that says t pointer size equal to something. Tell me exactly what that instruction is.
Is it 1 plus t of left and t of right?
That's right. So all you have to do is, instead of taking the maximum and then adding 1, you have to add the size of the left subtree plus the size of the right subtree plus 1 and set that to the size of T. Is clear? That's the definition of size, right? Size of a node, a tree, rooted at a node is the size of the left subtree plus size of the right subtree plus 1. So that's the extra line of code that you have to write here. Okay. Now let's go back and look at these four functions. In fact, we are going to look at only one of them because the second one involves two calls to this. Yeah. And these are just mirror images, so you have to do that here, but the code is not here. So, okay. So there it is, right? So there's one place where k of height is adjusted here, right? So immediately following that, you have to write k2 pointer size equal to, and then write an appropriate formula. Same way here, there is an adjusting of height k1. And immediately after that, you have to adjust the size of k1. That clear? So you have to add two more lines. One immediately after the statement k2 pointer height equals ... And then you have to write another statement immediately after this one that says k1 pointer size equal to. Okay? And that's it. Okay. That's all you have to do for this whole project. You're almost done now. Only thing that's not shown here is rotate with the right child. You have to do exactly the same thing like this. Okay. And then we're going to spend the next couple of minutes talking about exactly how you're going to report what you've done. So there is a main function where you have to randomly generate a large number of keys, and then you're going to basically perform a series of operations, and then you're going to report some median value. So basically what you're going to do is you're going to create, let's say, n keys randomly, and then insert them into a binary search tree, and then report the median key. Then you're going to delete the, half of the higher half of them, and then report the median of the remaining half. How do you know which is the higher half? Well, to do this, what you're going to do is, when I say higher half, I'm sorry, I have to take back what I said. It's not the key of those ranks. What you're going to do is you're going to generate say n keys randomly, and then store them in a vector, okay, as you are inserting them into a binary search tree. Okay. And then you're going to report the median of the entire population once, okay. And then you're going to remove the upper half of the number. That is the numbers that are in the vector from index n/2 plus 1 up to n. After deleting those half of them, you are left with the binary search tree or Avl tree with the first half of the numbers. Then you're going to report the median of those numbers. That's it. Okay. Is this clear? Okay. I think that's all is there to this project, and we'll stop the recording now. And then if you have any further questions, we'll talk.